Hello, hello. It is time for lecture 13. If your screen is flipped, then it's time for lecture 13. Hi, it's so good to see you. I hope you've got your study guides out and you're starting to do your preparations for all the writing and stuff and taking your notes. Remember, the study guides are a guide for you to study. That doesn't preclude you from taking other notes, right? Because all that notes, it's important in our conversations as we're moving forward through this wonderful part of physics that we're getting to. There's so much good stuff that I cannot wait to share with you all. I wish we could spend even more time going even more in depth, but our point in this class, remember, Physics 1, is to set you up so that you have the physics that is useful for what you're doing going forward, right? Now, remember, our physics class here, this Physics 1 class is most of you are not planning to become physicists, but you are going to be using a lot of physics in your careers in your fields. For example, things like in the biological sciences and the health sciences and things like that, right? So instead of going too much more deeply into some of the things that we've been getting up to this point, right, this semester with all the torque and the motion and the rotation and the acting and things like that, which is all awesome and could be gone into in great depth, we're going to continue forward in our path about physics to get to the next level of the things that would be useful for you. In other words, when we take those basic ideas of motion, right, Newton's laws and energy and trajectories and rotation and those kinds of things, we're going to take it to the next level and move on to the next kind of using that stuff, but in systems, not just isolated like objects, like things running into each other or sliding and things like that or spinning, but actually more complicated system when you have materials, fluids, substances, things like bones, structures moving around. What are the kinds of things that we have to be aware of, and how does physics work in those environments? So this is where we're going to be launching on the next few lectures, starting with that next level of the energy. And we'll use that as our way into these systems of fluid and all that kind of cool stuff. Okay, so let's do it. Are you ready? Yes, I am too. When we left off, we were just talking about the different kinds of energy that we get, right? Energy that makes what we do possible, that does the things that we need, right? So let's recap. I'm going to take this nice big back of an envelope to recap the cool kinds of energy that we've been using all this time. You remember my trusty water bottle, right? This one here, which I've been dropping and so forth, right? It's about 1/5 full, so it has 100 grams in it, or 0.1 kilograms. And then I've been doing all kinds of things like explaining how much joules are when we've been dropping them or lifting them and things like that, right? So remember the gravitational potential energy, the kinetic energy, things like that. So I'm going to write some of those equations down. EK equals 1/2 mv squared, right? The kinetic energy of a system. If an object is mass m and it's moving at a velocity v, you square the v, so then it no longer matters what vector v has, right? And then you wind up instead getting a magnitude v squared, so it's a scalar. And remember, we talked about how you basically are increasing the amount of momentum each time you increase the velocity a little tiny bit. And eventually, sure enough, the area under the curve of the map of momentum, right, velocity, you wind up getting kinetic energy, which is really kind of cool. It's basically the thing that accumulates, or the thing that is the measure of the change in momentum of an object, right? Kinetic energy. Now, there was also the idea that the potential energy, in order to get something to turn into motion, we have the potential energy of an object, right? Which broadly stated was force dot distance, right? This dot, as I've told you very briefly, and you don't have to worry about this because this isn't a vector calculus class, is a dot product, which also turns vectors into scalars. Sometimes have to worry about certain directions of what's going where and so forth because there was forces, and you've watched some of those videos that sort of explain that difference. So I'm going to put the vector marks up at the top, but realize that when we use this dot product or we use multiplication, we're caring more about the amounts and the directions, the magnitudes, right? And what angles are involved and so forth. So that's a kind of thing that you want to calculate. But I put it out this way in general because many of you are able to absorb the larger concepts. Remember, this class is more importantly about the concepts of Physics 1, and you can do the calculations, but that's secondary, because if you understand the concepts, then the calculations just sort of show up if you practice enough. Okay, so, or if you look them up, which is also allowed, right? This is the 21st century. It's kind of cool. So force times distance, right? In a vector way, force dot product of force and distance. And it turns out that if we're looking at a gravitational system like the Earth, right, we can think of this force as the force of gravity times the distance at the amount we fall, right? And so very often in physics classes, and if you've seen this in the textbook already, is mgh, right? mg being the force of gravity at Earth's surface, g being the gravitational acceleration of the Earth, right? And then m being the mass of the object that's falling. And you take that in that gmm over r squared thing, which we're not worrying about in this class at the moment, but then you multiply it by the height of the object that falls, right? Or the height of the motion. So you take this water bottle and the mass of this water, right, times the gravitational acceleration of the Earth, which is about 10 meters per second squared. And then I lift it 1 meter, right? So mass 0.1 times 1 meter times 10 meters per second squared, 9.8, whatever. And you wind up with a joule. So if I did this and lifted it up here, I get 1 kilogram meter squared per second squared, which is 1 joule. And if I drop it, right, I get 1 kilogram meter squared per second squared of kinetic energy, because that potential energy going up drops down 1 meter. And actually this the speed, you can make that calculation of how fast it is and things like that, right? That's pretty cool. So we had that kind of thing. And then we had the rotational energy. Remember that? And just as a quick reminder, we can do that as well, dependent on your moment of inertia, right? E sub r or E sub theta. And you saw these equations in the textbook stuff that we're talking about in the previous lectures and so forth, right? The rotational energy, and it's very similar to the 1/2 mv squared. Instead, we call it the 1/2, right? I, the moment of inertia, and then omega, right, which is the angular velocity, how many radians per second the thing is spinning. I omega squared is another way of figuring out the kinetic energy of something that's spinning around and around and around, right? So these energy equations are great because they sort of talk about the energy of your motion activities, whether you're spinning or moving straight up and down, moving at any speed, moving against a force, right? Those kinds of things, that's all part of the combination of energies. Now we're taking it energy to another level, an almost invisible level, a level that's really hard to understand until maybe 100 years or so after Isaac Newton first did his laws of motion, after we had this concept of this energy that we could get from motion. And that's the energy of motion that we couldn't see with our eyes, that we couldn't manipulate with machines that were the size roughly of us humans and things like that, right? What is that energy? Well, it's the energy that is in us right now. Every single particle of our existence, all of our bodies, all the blood in us, all of the sinews, or all of the bones, or heck, all of the particles in our air, right? They are all moving. But this motion is not especially useful. It's not getting, for example, like this fingertip from here across the room, right? I pointed this way, but it just stopped kind of there. The energy instead in here, all these little particles are doing the dance. Get down tonight, right? They are jiggling and wiggling and vibrating and rotating and doing all kinds of strange, they're basically moving in place. Every single little particle in our space is moving in place. Yes, there's nothing we can do about it. It just happens. That's actually a good thing, right? But what it means is that there's a lot of energy that's hidden in there. Imagine if I'm talking about a little tiny particle. Okay, this is just a thought experiment in my head. Let's say this little particle is moving, but it moves like a tiny fraction of an inch left, and then moves a tiny fraction of an inch right, moves a tiny fraction of an inch up, and then a tiny fraction of an inch down, tiny fraction of an inch forward, tiny fraction of an inch backward, and then keeps doing that. Right? In the end, there is kinetic energy involved, right? It goes here, there, up, down, left, right, up, down, up, down, There's a lot of energy there for that particle, a lot of 1/2 mv squared. But in the end, it's not getting you from point A to point B, right? That velocity, because you're squaring it, right? You don't worry about the vector anymore. So there is energy in there, but it doesn't go anywhere. So it just sits there. And that's why we can't tell it's there usually, right? If I'm sitting here, can you tell that I'm brimming with energy? I'm just brimming with energy. Oh, yeah. You can tell from my facial expression, just drooping with joy. Yep. See, you can't tell, but that's okay. Actually, there are ways to figure out. But it took a century or more for people to realize, oh, there is energy there. How do we measure it? How do we count it? How do we figure it out? Okay. And so therein lies this next part of energy conversation that we're referring to, when the energy escapes and it goes and hides somewhere in the random motions of our bodies, okay, of any body, any object, anything. And so I'm going to put this aside for a second. I'll probably do some annotations about this, but we're going to add in a little while like the kind of energy we're talking about and how that energy gets moving around. So the problem with that kind of energy, all right, and you might already know what I'm talking about. I'm kind of talking around it because I don't want to use words that are familiar yet to define certain things because that will wind up confusing us. I also want to start from first principles on the concept of this kind of jiggly, jiggly, wiggly, wiggly energy, right, that I wanted to show you now because, well, I want you to think about it in terms of physics as opposed to in terms of, say, your preconceived notions of stuff. And the problem is, I mean, preconceived notions are fine. It's easy to sort of eventually get over them, but it will lock your brain into thinking about ways that have very difficult boundaries for you to break out of. So I want you to try not to have those misconceptions as I talk about this kind of wiggly jiggly energy. Make sense? This wiggly jiggly energy, which we know is hiding in there, but we can't measure it effectively because we're not taking it from here to there, right? So let's think about how we're going to measure it. The key about this kind of wiggly jiggly energy is that I can't figure out exactly how much is in there all the time, right? I can't tell how much energy is in my cheek muscle right now. What I can tell, and what the scientists, people like James Joule and Ludwig Boltzmann and people like that, these names that you might come familiar with at some point later on, what they were able to figure out was the change in the amount of energy in my cheek muscle, right? This cheek muscle is what I was pointing at earlier. I can't figure out how much is in there at this moment, but I can do something to this cheek muscle that then I can tell, oh, there was a certain amount of energy that was transferred, right? That was changed in the system. So I don't know exactly how much is in there sitting there resting, but I can move it or I can do something to cause those little things to jiggle and wiggle and squiggle more. And therefore I can figure out how much energy is caused by that change. So you see, this kind of energy became known or measured by the amount of change, how much was moved, how much goes from here to there, right? And how that gets transformed. It's kind of complicated, but again, conceptually speaking, it makes sense that this was harder to learn because instead of being able to measure very clearly, well, this had no kinetic energy because it's not moving, and now it has kinetic energy because it's moving, right? Now we're talking about this object, this cheek muscle, whatever it is, has some energy. We don't know how much is in there. But if we add a certain amount of energy, then we can see the effects of it. So that kind of change in energy, that kind of transfer of energy in these subtle and ways that aren't having to do with large motions of individual objects and so forth, became extremely important in understanding this kind of energy. And so the thing that people were able to measure the change of was something is basically how much jiggling, right? The average amount of jiggling that my cheek muscle particles do. That average amount of cheek muscle parting moving is something that we use every day, but you might not have realized that that is what you've been measuring all this time. Okay, what have you been measuring? You have been measuring this quantity, this extra jiggling. How much jiggling is going on per, particle, something like that. And that kind of concept, that jiggling concept, is known as temperature. Okay, temperature. So physically speaking, temperature is basically how much, a measure of how much of this random, this not work producing, but still perfectly existent motion is going on in your body. Okay, so temperature, you have measurements of different levels. Okay, you can imagine a temperature where there is no motion at all, no jiggly wiggly wiggly jiggly. Wow. But then there's me, right? And my cheek muscle, which has some jiggly wiggly 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 motion. And you can imagine something like a blast furnace, where the atoms and molecules that are inside the blast furnace, right, is being stoked at great temperatures, is going really fast, right? And so what happens when you have this kind of temperature thing going on? That's a measure of how much energy is sitting inside your systems. This is not a deep concept until you realize that you can't see this jiggly wiggliness, right? Without microscopes, even with a microscope, you can't see all these particles moving. So it's actually really complicated. And you have to think about them in large groups. Okay, you have to think about these concepts, these particles, not as a few particles wiggling and jiggling at a time, but millions or billions or trillions or quadrillions or quintillions or sextillions of these little tiny objects moving around like crazy, right? That's really hard to think about. Therein lies the problem that we're working with. Okay, so if you have something with a temperature, then you can say, okay, how much energy is in a substance if I change the temperature? Remember, I can't see how much energy is in there right now. If I were able to remove all of the wiggly jiggliness, right? Take zero temperature of absolutely nothing, then I can start adding it and go up and up and up. But you know what? You can't get down to that temperature. Certainly, you can't get down to close to that temperature until the 1900s. And then even in the late 1900s, it was shown conclusively, despite however equipments we can go, we can get to very close to that absolute zero, but we can't actually reach it. Okay. Now that's a sophisticated aspect of temperature and the kinds of things we're talking about this kind of temperature-based energy, which we will talk about later in the semester. Not too long from now, but not at this moment. Okay, so this temperature thing, all right, we have to think about materials. And we realize that each material holds a different amount of heat depending on what the temperature is. I've given it away. The amount of energy, right? The energy that is put in to change temperature is heat, right? And so try to think about heat at this moment, right? Not about the concept that you've thought about since you were a kid, about like what's hot and what's cold and things like that. But think of heat as a kind of energy, specifically a transferred energy, energy that moves from one place to another, but subtly in ways that are not like moving an object from here to there. Okay, so heat is the kind of energy we want to talk about in this case. So objects, materials, my muscle, that water, things like that, they have different abilities to absorb heat. If you put a certain amount of heat in this cheek muscle, I don't know how you get heat in the cheek muscle, right? If you put that a warmer next to my hand, right? What will happen to this material in the cheek muscle? How much heat would I put into it to cause the temperature to increase? How much heat do I take out of it to make the temperature decrease? Same is true with that water over there, that water bottle, right? How much energy do I have to add in here to make all that work? So there is a formula. Of course, there is a formula. The amount of heat that changes. But remember that heat, right? Because we've talked about energy here. And this energy stuff, we've been talking about how much energy is in or in out. Now we're talking about changes in energy, right? So instead of using the just E by itself, I start using delta E, which is the change in energy. Make sense? I'm going to start talking about changes in energy. Now, the textbook uses a letter Q, okay? That's commonly used, especially in like chemistry. Very often heat is, the change in heat or whatever has to do with chemistry or any kind of other kind of changes. We often use the letter Q. But I'm going to stick with the E thing. So we're going to stay consistent with the physics. But in the textbook, remember, conceptually, Q and the change in energy, right? Basically the same thing, delta E. So I am now going to write down a new equation. It has to do with heat and how much heat something can store or be stored, right? This is probably something you've seen before in your other classes, in science and so forth, but it has to do with heat capacity, all right? So I'm gonna write this down here. You know what? I'm just gonna write down this delta E, just so you know that it's kind of there, delta E. And remember the capital delta, right? The capital Greek letter delta means change in. You've probably seen that before. If you're doing calculus, then you might see a lowercase d, and the dE becomes the differential amount, right? Which we're not dealing with in this class, so don't worry. But if you ever do it, and you see a little dE or a dQ or something like that, doesn't mean Dairy Queen in this case, especially if the front D is a lowercase d. It means that it's a change in something like energy or something like that. Okay, does that make sense? So here's what I'm going to show you. This, I have a backup envelope already prepared. Heat capacity and then heat transport. Okay, I'm going to talk about heat capacity right now. We'll talk about the heat transport in a little bit. The amount of change in heat, right, this energy, is the mass of your object multiplied by this heat capacity per unit mass times the change in temperature, delta T. See, the delta, again, change, and then T is temperature. That temperature scale we're referring to. Or we can talk about volume. So heat capacity per unit volume. Let's say I have a certain amount of material, how much of it is there and how much volume is it? And given that material and that volume of material, that's how much heat can be contained in that given volume. Heat capacity, how much it can be contained in a certain amount of mass, which kind of makes sense, right? So heat capacity, we'll talk about heat transport later. Like I said, heat capacity, delta E equals mcm delta T, or V C sub V delta T. We're mostly in this physics 1 class going to use this mcm delta T. Okay, that's heat capacity. Good stuff. Yeah, I got to measure that temperature thing. I happen to have another cool body temperature. Body temperature is used in very different scales. You've probably heard of these kinds of scales of temperature before. Remember, temperature, trying to measure that absolute zero, really hard, right? But a guy named Kelvin, you've probably heard of him before, William Thomson, Lord Kelvin, figured out that there was indeed an absolute zero, not by reaching it with an experiment, but by doing theoretical calculations based on other people's experiments over long periods of time. All right, people did a lot of experiments. Galileo, for example, that inertia thing dropping from our Pisa scientific method, all that sort of stuff. Galileo did experiments, built one of the first thermometers that had to do with heat capacity and sizes and things like that, and how things get more or less dense depending on their temperatures and so on. And Mr. Fahrenheit, there's a guy named Fahrenheit, yes, there is, Fahrenheit, who actually used a temperature scale to try to figure out what the temperature of something was based on stuff. And he wound up coming up with a scale. And then Mr. Celsius also came up with an idea, a way to measure temperature, right, with different scales. In the study guide material, you're going to learn about these things and kind of remember how these things work. And then Kelvin based his, right? That's why we have the F for Fahrenheit, C for Celsius, and K for Kelvin. C, by the way, also sometimes stands for centigrade, because the way that the Celsius scale works, at the surface of the Earth, 0 Celsius, right, to 100 Celsius is the difference between the melting point of water and the boiling point of water, which is kind of cool. So to divide it up into 100 pieces, that's why it's centigrade. See, clever. Anyway, Fahrenheit, centigrade, and Kelvin, right? With Kelvin, 1 degree of change in Celsius is equivalent to 1 Kelvin change, but the 0 point is different. Remember, 0 for Centigrade is at the melting point or the freezing point of water at Earth's surface. And 0 point in Kelvin is all the way down when there is no temperature at all. Temperature is 0, right? 0 Kelvin is absolute 0, no jiggly wiggly swiggly at all. So these three numbers are the same. You probably knew this already, but just in case you didn't, it was good to know, right? And then we have the heat capacity of water, because we use water a lot. So I'm going to use water a whole bunch so you can get used to this. 1 calorie per gram. Now this stuff down here, okay, has to do with radiation. We're going to talk about that in a short time. So I'm just going to go like that. Not that I'm holding out on you, but it's just that we'll get to it later. Okay, so don't want to confuse you on that. So the heat capacity of water, we use that a lot because it's a convenient number and it's kind of useful. And early on, scientists tried to use water because it was so common and so useful as a way to sort of calibrate all of our different ways of measuring temperature and heat and things like that. So you've probably heard of the term calorie, right? We've talked about that. And so 1 calorie of heat energy is stored in every gram or added to every gram of water every time you add a degree Kelvin, right? Now, we were talking about joules before and calories, right? The calorie turns out to be 4.2 joules. If you're trying to convert from heat into mechanical energy, 1 calorie is 4.2 joules. If you live somewhere other than the United States, very often your food will be listed in kilojoules or in joules or kilocalories, as opposed to kilocalories. Okay, it's kind of interesting. You can often see labeling in 2 different kinds of energy units, but they're exchangeable that way. And then remember that since water has a density, right, of 1 gram per cubic centimeter, the volume-based heat capacity of water also happens to be 1 calorie per cc or per cubic centimeter per degree Kelvin. So if you add a degree, if you make the temperature of water go up by 1 degree Kelvin, you have a certain number of grams or something like that, then you wind up adding and creating a certain number of joules or calories that have been put into that system, right? So this is thermodynamics. It's kind of fun. It's the beginning of the concepts of heat and heat capacity and so on. And I want you to get used to it because it's fun. Let's go to the college physics textbook. I want to point out to you where you can look up more of this stuff. And remember, in the study guide, this is where you're going to start practicing and working on all this cool stuff. All right, go back to our friend College Physics. Remember, here's the URL if you need it. Again, and we did all this great stuff here, right? Uniform circular motion, work, energy resources, momentum, torque, things like that. We got through all that stuff. Oh, this is great, by the way. We're going to get to the fluid statics in a very short time because we're talking about water, right? And this is going to get onto our system very, very soon. Temperature, kinetic theory, and gas laws. All this stuff is going to be really important for you in a very short time because that's the extension of chapter 14, heat. Haha, right? I want you to read this introduction to heat and heat transfer methods. I use the term heat transport, which is kind of basically the same as heat transfer. The textbook scientists who wrote them decided to use the term transfer, which is 100% fine. But see, this chapter is really, really cool. It talks about heat and what it means, and defining heat as a transfer of energy, actually like true energy stuff. And we talk about changing, right? So read this section 14.1. We're talking about energy existing. It's just a very basic summary. But for this section here, we're going to talk about 14.1 and 14.2. In the next lecture, we're going to talk about 14.3, this latent heat stuff, and then move on to 14.4, 5, 6, 7. This is all great stuff. All right. Definitely you want to know it because it's that much fun and it's neat. We're going to get into that probably in the next lecture. We'll get right to it. But for this particular one, I want you to read this carefully. I want you to get a sense, okay? Read what heat is, and heat is calculated and how it's working on, right? Just in all this sort of stuff. Temperature, right? Which we talk about here in our effort to get to heat, that temperature is like the average kinetic energy of atoms and molecules moving back and forth, not really getting anywhere, remember? So this heat, that's transfer of energy due to a temperature difference, and then there are kinetic energy, gas laws, and things like that. Remember that heat and temperature are not the same. I've been trying to tell you that all throughout this point. And instead of trying to, use the term heat and then use the word temperature and then tell you they're not the same, I tried to tell you temperature first and then tell you what heat was in the context of temperature. Hopefully that helped you figure out what's going on. Anyway, this is really nice. And then you have this equivalent of heat. See, 1,000 calories is equivalent to 4,186 joules, right? And remember that thing that I was holding up before, which is probably too small on your screen right now to see. I gave this two significant figures, 4.2, right? 4,200. So if 1 kilocalorie is 4,200 joules, 1 calorie is 4.2 joules. And I'm going to use the small calorie often because we often in the biological sciences care about how many cc's or how many grams of water. We typically don't use entire kilograms worth of water, right? We use just grams because like our bodies and so forth, we're doing, we have to drip 3 cc's of this and that into this and push 4 cc's of that into that person, that kind of thing. So cc's are very commonly what you're likely to use, but you can make this kind of measurement. And I want you to read this and understand how James Joule, the guy who like we named Joule after, right, the energy, how he sort of figured out that heat is basically the motion of energy thanks to temperature differences, right? And so here, heat transfer. This is how we're talking about how heat moves from one thing to another. And the concept of heat capacity is described here. Remember I was telling you about Q, right? We use delta E, but it says MC delta T. And notice that he doesn't have that little M at the corner of his heat capacity. I prefer to put it there so keep it not confused with other things with letter C, such as the speed of light, which you will get to at some point in this class too. Oh man, there's so much cool stuff in this class. I can't wait to tell you all about it. There's so much to do, but reading this will really help you. So calculating the heat in an aluminum pan, okay, and this is important, and go through this and understand how this is. And in the study guide, you can expect to do some of the work on this kind of work, right? And 14.2 about how you transfer mechanical energy and turn it into heat energy. And here are some heat capacities, right? Now, the specific heat capacity here, like the C that is referred to, right? Sometimes you turn, you have for solids, something like aluminum, or metals. Notice that their heat capacities aren't that high, right? 0.2 kilocalories per kilogram per degree Celsius, or in our case, right, calories per gram, same kind of thing. And then multiply this by 4.2 and you get the number of joules per gram. 0.9, right, or it would be the number of joules, 900 joules per kilogram. See how these units work, right, back and forth. This number is basically 4,200 times that number, give or take, something like that. But you can see how there's a variation, right, of metals being relatively low heat capacity. Glass, relatively, look at gold. That doesn't hold heat very well at all. No, it does not. Look at the human body, though. It's pretty high. It's 0.83 calories per gram. Right? And so that's getting pretty high there. Well, why is that? Well, take a look. Water, 1.0. That was exactly what we were talking about. 4.2, right? Or 4,200 joules per kilogram, or 4.2 joules per gram, or in this case, 1 calorie per gram. So really, look at that. Water actually stores heat really, really well. Under most common substances, the things that we contact with on a regular basis, water has great heat capacity. So that's why water is in part so useful in things like when we're cooking, right? If you're cooking a pound of pasta, all right, the heat gets stored in your water really well and gets transferred into your dry pasta, and that will help cook the pasta. That's kind of helpful, right? So it's really helpful. The human body is mostly water, which is probably why the human body has such good heat capacity also, right? 83% that of water. And then ice is only half of water. Isn't that interesting? Only about half as effective in storing heat as water. So heat transfers through, and you can't hold a whole lot of it. Well, wait a minute. Ice is solid water, isn't it? Huh. What does that mean? We'll get to that in the next lecture. So here's another calculating final temperature while heat is poured in different bodies, right? There's the hot and the cold and the changes and the numerical values. This is kind of cool, right? Very often this kind of thing about heat capacities and so forth and so on is covered in a chemistry class, right? Because chemistry is all about like what happens when heat does this to this chemical or to that chemical, how much heat is released, how much heat is used, how much heat is stored. Chemical potential energy is basically heat locked one way or another in chemical bonds and things like that. So chemists are really, really, really high on heat. All right, they big time heat. But remember, actually speaking, heat is a physical quantity, right? Physics is what explains what heat is. The motion of all those little tiny particles in a big system, right? And the kinds of ways that that energy moves from one place to another is basically if there's a temperature difference, then that heat will move, right? And if there's a temperature difference and the heat moves, what happens to the whole system? How do we get that heat out? How does the heat heat us? How does the heat cause our metabolic processes to work? How does the heat actually allow us to move our arms? That is the next step as we're going forward. We're going to talk more about heat and heat capacity. But for now, it's the end of this lecture. Read the stuff. Hope you've been writing down cool stuff about the lecture guide, study guides rather, and doing the lectures and doing the work. Yay! Thanks so much for your time. We will talk again in the next lecture. All right. If you have any questions about this, remember they only talked about one equation really in this class, in this particular lecture, but that energy change can be used in a lot of other different ways, right? So the transfer stuff, you can expect this delta E, which we had talked earlier about, E equals mc delta T, right? That's on this part, right? Heat capacity here, not about heat transport just yet, right? mc delta T, or MCM delta T, in my case, delta E. We're going to be filling that in here and making the equation here complete, and then start moving energy around and talking about how that influences all of physics. Very, very cool. Anyway, thank you so much for your time. Do those study guides. I'll see you in the next lecture. Thanks.